Today, this lecture is important in the sense it may be. I hope it is exciting still, but it will be maybe less exciting than the previous one in terms of the foundational stuff that comes from the beginning. But it's important from the workhorse stuff, as in like dealing with a little bit more concrete and dealing with the particular things that we're going to be using in the course as tools. And again, you're going to have both homework and a tutorial about this stuff. Okay. All right. So we have quantized the field, and we have introduced, remember, to the classical theory, an extra structure allows quantization. That was the complex structure. We have quantized the field. We have talked about unitarily equivalent and inequivalent quantization. We have talked about the fact that the vacuum depends on the quantization. And different quantizations, even if they are unitarily equivalent, where the physics is unambiguous, right? No matter the quantization, you still get things like the notion of particle is quantization dependent and therefore perhaps observer dependent. The notion of vacuum is obviously the same. Okay, so in doing so, we talked about several two-point functions, and two-point functions are going to be important. They are important objects of the theory for several reasons. Whether you look at things perturbatively and they play a fundamental role, or you look at things from the perspective of Gaussian states, as we will discuss a little bit, two-point functions are extremely important objects. And you probably have seen, I assume, two-point functions here and there in different courses or in talks or in research topics that you've seen. So we're going to discuss a little bit the most common two-point functions and the ones that are going to be helpful for us. That makes sense? Now, of all these objects, how many sound familiar from outside of this course? How many of them have you guys seen? Well, the Weinmann function only in this course? The Hadamard, I assume same. Pauli Jordan, you certainly have seen the Pauli Jordan. You've seen the commutator. That's the Pauli Jordan. Remember, the Pauli Jordan is the commutator. Okay, well, the commutator, the expectation value of the commutator. Pauli Jordan is cool. It's within the classical theory. It's state independent. Well, once again, it's the expectation of the commutator. Okay, so you have seen that before. Maybe you didn't call it Pauli Jordan, but you've seen it before. Now, retardant advanced green functions you have seen. No? Both Pauli Jordan and retardant advanced green function, as well as the symmetric propagator, they are part of the classical theory. Okay, they are. You don't need the complex structure to define them. Now, certainly you've seen the Feynman propagator. No? It's kind of funny, huh? You see the Feynman, and you don't talk much about the Weinmann. So, okay, phi expectation value is fine. It's not fine, but T phi expectation value is fine. How's that? Anyway, so yeah, you've seen the Feynman propagator, all right? So we're going to do a bit of a deep dive on them, and also we're going to see what they look like in the case of Minkowski. In fact, your assignment is going to contain to derive the expression. I'm going to show you expressions. We're going to discuss those expressions and the distributional nature, but your assignment is going to be to deduce those expressions, including a bonus questions about how familiar are you or how used are you to working with distribution theory, distributions in general. Some of you more than others, I assume. Yeah, this assignment is going to make you practice, but it's guided, so don't worry. And please ask questions. Ask Irini about the assignments, anything. She will be here, not today, but she will have her own office hours. I was hoping to announce it today, but she's away. So next week, she will have office hours. She may be here as well on Wednesday when I do mine, like after the lecture. But also after the tutorial, before the tutorial, she can stay as well and take questions. But it's all guided, and I will introduce some things here, so hopefully it won't be too bad. All right, so let's talk about the Weinmann first. The Weinmann is, I would say, the mother of all two-point functions in a way. No, it's just the correlation, is the two-point correlation function of the vacuum. Well, we're talking about the vacuum Weinmann. Technically, there's an abuse of language often. When I talk about the Weinmann, we mean usually of a vacuum state. But then again, the vacuum state depends on the complex structure. Any pure state can be a vacuum to some complex structure. So technically, you can call it Weinmann for any pure state. And we often abuse it also. If we have a mixed state that is not the vacuum, right? We do say that the two-point function of that, we call it W, and oftentimes people say, oh, it's a Weinmann. But that's an abuse. Technically, the Weinmann two-point function is related to a vacuum. And if you're in Minkowski, okay, that vacuum, you know what it is. It's a vacuum that has all the symmetries. The vacuum associated with the complex structure that I mentioned the first day, right? The one that has all the symmetries, Poincare invariance, etc. Anyway, the idea here is a two-point function, is the two-point correlator. Obviously, in the vacuum, or at least in a vacuum associated with the same complex structure that you quantize phi, you would get, this is literally the correlator, because you would have the correlator is that minus the product of the expectation values of the amplitude, right? Expectation of phi x, expectation of phi I. But in the vacuum, that's 0. So this is literally the two-point correlator of the field. The two-point, pick the field in x and y and how correlated they are. What is the correlation function? So that's what it is. Make sense? All right. So the real part is the Hadamard distribution. This we saw already. This is part of the classical field theory part that we saw, right? That the Hadamard is actually defined, if you want, as the real part of the Weinmann function, and the Pauli-Jordan is the imaginary part of the Weinmann function. Now that's kind of easy to see, right? If you take, it's probably another slide, but let's do it for fun. You can divide this into a symmetric plus an antisymmetric part, no? The symmetric part is the expectation of the anticommutator and the antisymmetric part is the expectation of the commutator, right? Agreed? So again, we already know that this is the Pauli-Jordan, but it's easy to see that is certainly the imaginary part of the Weinmann. Okay, maybe I'll do it like that. So if you want to do, I'll try something. Oh, this one doesn't move. Okay, very sad. I wanted to put it up. We can't compute this guy, no? What is this? Well, this is going to be, ow. Right? Okay. So we write that, and we get that this is 0. This board is less ideal than the other one. Can you see still what I write? I see. Thank you. Oh. You're gonna have to turn it off afterwards too. I appreciate it. Right. Well, of course I forgot the factor. Right. But then we look at that. What is the complex conjugate of this? Well, the complex conjugate of this, just swap the two operators. Agreed? Right? So first cool thing, right? This is the Weinmann. This is the Weinmann star. Well, this is the same as swapping the arguments of the Weinmann. Agreed?
Does that require the fields to be like observable?
Yeah. Those are real. This is a real field. Yeah. If not, the Weinmann function would be with the conjugate of the field if it's a complex field. Yeah, okay, question.
Minus the W.
Jesus. Thank you. Otherwise, how am I going to get the commutator? Thank you so much. All right, makes sense, everybody? Right. Thank you for checking my arithmetics. Arithmetic is not my field of expertise. Yeah?
In general, like, is phi always a scalar field for the Whiteman? Or
No, this is for, well, in general, this is a Weidmann function. Yes, if you had a vector field, you would have, it would be a Weidmann tensor, if you want. You get to that one direction associated with the field first field amplitude, so you would have two indices, W mu nu, right? And then you have the vector field, whatever you want, a mu and a nu at different points. This is because it's a scalar field. Anyway, so you have this, right? First of all, so you see that the Weidmann is equal to the conjugate of swapping the arguments. But then, of course, we can rewrite this. We can take common factors now as phi x prime minus phi x prime phi x. And of course, this is nothing but 1 over 2i, the expectation of the commutator, right? On the state here. Make sense? Yeah.
There, you define the Weidmann function using the field operator and the vacuum state.
Can by the way, can we turn the lights in the meantime?
Yeah, earlier you defined this using the
Complex structure.
complex structure. So are they the same?
Literally, yeah, they are exactly the same.
So can you?
In fact, part of your assignment is going to be to prove that. Can you say again?
Yeah, I see.
You can. I can show you, if you want, at the end of the lecture, I can show you the actual derivation. Even though I asked you to do so, I can show you the actual derivation so you see. Because I think that one is a bonus, the part for the Weidmann. I think I asked you the Pauli-Jordan in the homework, but I can show you the Weidmann. Yeah. You can compute. You can, in the end, this is equal. So classically, remember, is that we got that it was the, you can actually tell, okay, even easier. You can, the phi, right? Remember that how we, in the classical case, the Weidmann was the integral, right, over the product of plane waves. Remember that? Yeah, well, maybe I can recover that. It should be classical field theory should be 2. No, that's 3b. No, 4. Still no, 5. Yeah. So if we go to the Weidmann function here, you see what the Weidmann is from the complex structure. We define it, first of all, we define it as this, let me just do full screen. We define it as I projection of the Pauli-Jordan, and then one finds, doing this projection, I mean, first of all, you need to prove that to compute that, that's what I asked you in the homework, prove that the E is the sum of the imaginary part of the plane waves, and therefore the W is the sum of the plane waves, like this. So you see it's plane wave times plane wave conjugate at different points integrated, right? But if you go back, and now you go to the other expression, the quantum one, not this one, right? And then you say, okay, let's compute it. I can write phi as a mode expansion over the plane waves, right? Remember, with the A psi I, A dagger psi star I, right? And then now the A and the A dagger are now operators. It's A and A dagger operators, right? So you substitute those there. And then you get the first one. Okay, the one that survives is the one that goes with A dagger. The one that goes with A daggers goes with the conjugate of the plane wave. On the left, what survives? The one that's going with the A, right? Otherwise annihilated. The one with the A dagger would annihilate from the left. So the one that goes with the A is the plane wave. So you get the integral, because the field is an integral over all those. So you get the sum, right, over all the modes of the plane wave and the plane wave conjugate, exactly as the classical case. See? I mean, again, you're going to do it in the homework, but can you see?
Yeah.
If you substitute the field as a mode expansion in terms of plane waves, you get exactly the same expression as in the classical theory with a complex structure. It's kind of nice, right? Because you see that object, and then you think, it's a very quantum object. It's the vacuum two-point function. And then you think, well, not quite. It's already in the classical theory with a complex structure. Make sense? I did half of the homework, right? Not really, but a little bit. It's a tiny bit. You have the homework is long, so I don't feel any bad. Okay. Make sense, everybody? Do we like the Weinmann? The Weinmann is great. The symmetric part of the Weinmann is the expectation of the anti-commutator. The antisymmetric part of the Weinmann is the expectation of the commutator. It's related to the Pauli-Jordan, etc. All right. Well, in fact, I kind of do it here. So you see the Hadamard distribution is the symmetric part. So we're going to discuss this more, okay? It says this means it contains the local singularity structure of the state. That probably makes no sense until we discuss it a little bit. But let's commit it to memory and we discuss it a little bit. So one thing that you realize here is that if you look at the Weinmann function, although we will discuss it, if you split the thing that is hidden, this part is not really state dependent, no? Remember, the commutator of the field at 2 points is going to be proportional to identity. Agreed? The commutator is what gives the Pauli-Jordan. So that thing is proportional to the identity. Think of it as the following: the commutators between phi and pi are going to give you multiples of identity in a free theory. So this thing does not depend on what state you sandwich it with. It's going to be the same function. It's independent of the state. Makes sense. The Pauli-Jordan is classical. There's nothing that can depend on the quantum state of that. So the information about the state, what kind of state is that vacuum, is in the symmetric part. The antisymmetric part has information about the theory itself, the classical theory behind. Whereas this one has information about the particular state dependence, quantization dependence, if you want. And because of that, it's going to contain all the interesting information about the state and the theory and the quantization scheme, as we will see. But again, many of these things are kind of foreshadowing things that come later. So commit it to memory, and let's try to understand it better. And of course, we have the Pauli-Jordan, right? Which is, well, it depends how you define it, but if you have it like that, it's going to be maybe a factor of 2 missing, no? The missing. Yeah, no, okay, it's fine, because I define it like this. That's okay. So you see the Pauli-Jordan distribution is the antisymmetric part of the Weinmann function. So that the Weinmann can be written as 1/2 the symmetric part and plus 1/2 the antisymmetric part. Make sense? That makes sense so far. Is the same that I've done on the board. Okay, so H, by the way, is what we call the Hadamard. So the Hadamard is the symmetric part. Once again, the expectation of the anti-commutator with a factor of 2. And the imaginary part is the expectation of the commutator, which is state independent. And it's classical information about the theory. It's the mechanics part of the information, whereas the Hadamard is the quantum part of the information, or the 2-point correlator. Make sense? Yeah.
So you said like the Hadamard is the symmetric part. So then is the Pauli-Jordan the antisymmetric part?
Pauli-Jordan is the antisymmetric part.
Okay, so the antisymmetric part is all the classical information, and then the symmetric part is all the quantum information.
Careful with the words, they're loaded. But the antisymmetric part, it's only dependent on the classical theory. It's the commutator. It's the Pauli-Jordan. Remember, that was part of the classical theory, no need for complex structure. The symmetric part depends on the complex structure. Therefore, depends on the quantization. Therefore, it's got information about the quantum nature of the field.
Oh, okay.
All these words have to be qualified. The word is quantum or classical depends on the context you use it. Make sense? Yeah.
And so like the commutator brackets here, like still, like is it classical because it's following the same structure as like your Poisson algebra, or?
Well, it's classical because we had it already in the classical theory. Is the object, is the advanced minus retard, we will say here, the retarded minus advanced, right? And that is an object of the classical theory. It's what the Pauli Jordan, remember, is this magical object that takes the field at any point and propagates it towards the future. Take it for a Cauchy surface and propagates it towards the future or the past. It's part of the classical theory. You didn't have to let anybody in to get the Pauli Jordan, whereas to get the Hadamard, you needed to let in the complex structure to help. Make sense? So it is embedded in the classical theory, the Pauli Jordan, but not the Hadamard, and therefore not the Weinmann. Make sense? Good, good. Now, of course, we have our old friends, the retarded and the advanced green functions. Remember that the Pauli Jordan we already saw in the classical theory, it was retarded minus advanced. So certainly the retarded is just take the Pauli Jordan only in the future and make it 0 outside of the future. Take a point, take your point x to be the origin, okay? And then you point y, it's the coordinates, so the origin, say the g of 0 and e of 0, and then y. That would be the light cone in the future. The retarded green function has support only in the future light cone. The advanced has support only in the past. Make sense? Everybody? Okay. Then we have the symmetric propagator. The symmetric propagator is pretty interesting, right? We haven't been introduced to that, so I'm defining it right now. The symmetric propagator is the sum of the retarded and the advanced green function. And it's quite an interesting object. It's quite an interesting object. We introduced it because it's helpful and we're going to be using it. But it's kind of similar to the Pauli Jordan, no? The difference is the Pauli Jordan is kind of similar, but it's not. The Pauli Jordan has a sign in between the two. If the Pauli Jordan is retarded minus advanced, and advanced minus retarded. That means, oh, no, this is not. I don't know why. Oh, sorry. Give me a second. Sorry about this. It will be very fast. It feels like I added one equation to this version. And it was going to be nice, but somehow yeah, there you go. This one has it. Right. So again, what? I promise I saw it. Yeah, it is here. There we go. Right. So that means that we can write it as a sine function of the time coordinate. Like if you are, it's okay. The symmetric propagator. If you are in the future, then don't touch it because it's the retarded one. So it's the same. If you're in the past, change the sign. Make sense? So indeed, the symmetric propagator is a sine function times the Pauli Jordan. It removes the antisymmetry. It makes it symmetric again. Make sense? Hence the name of symmetric propagator. Okay, we have the Feynman propagator that we define in the classical theory, if you remember, as the time-ordered version of the Weinmann. So that means indeed that is if is the time-ordered version of the Weinmann it says literally, well, if x comes earlier than y, after y, then keep the order. If it's the opposite, swap the order. Remember, conjugation is the same as swapping the order. Make sense? So it's just a time-ordered. It's literally the time-ordered. If we were to write it, we would write it like this. The Feynman propagator would be like that, the time-ordered version of the Weinmann. Okay, so if this is kind of cool because if the Weinmann, remember, we could write as 1/2 the Hadamard plus 1/2 the Pauli Jordan, right? Then we can substitute the Weinmann with that decomposition here and see if you can write the Feynman the same way, as a function of the Hadamard and the maybe Pauli Jordan. And then what you get is that, so yeah, sure, you substitute, and then you get that the Feynman, so for W, you get is 1/2 h theta plus theta, and then, of course, the imaginary parts flip sign, though. That's the difference. You get theta minus theta. Agreed? So the sum of the thetas gives you 1. This covers everything. If you know the future plus something that is only true if one is before the other, plus only one is before the other, and only one when the other is before the one. The sum is 1. But the difference is literally the sine function. Using that, then you get that the Feynman propagator can be written as 1/2 the Hadamard plus I/2 sine functions E. But by definition, we already saw that's the symmetric propagator. So indeed, the Feynman can be written as the Hadamard plus the symmetric propagator, I the symmetric propagator. Yeah.
So the delta was time reversal symmetric, right?
Yeah.
And then E.
Well, space-time, full space-time symmetric. If you swap y and x, is the same.
Right. But in particular, it's also time reversal symmetric.
In particular, yes.
And E is time reversal and it's symmetric.
Yep.
And so then, what is Feynman propagator? Is it time?
It's neither, because it's got this part too that is symmetric.
But is there like a reflection on a complex plane or something? Or
You could think like that. So it's symmetric in the imaginary part. And it's symmetric in both. Symmetric in both. Okay, sorry, my bad. It's symmetric in both. Yeah.
Okay.
This is me looking at it right now. Sorry about it. I was thinking of the Wyman. The Wyman is neither.
Right.
The Wyman is symmetric in the real part and symmetric in the imaginary part. Okay, so interesting fact. Remember that I told you, without proof or anything, because I haven't discussed it, that this guy is the guy that has the singular structure, the interesting quantum stuff going on, is the same for the Wyman and for the Feynman. The Wyman and the Feynman have the same real part. Interesting, right? The Wyman and the Feynman have the same real parts. What changes is the imaginary part. The imaginary part of the Wyman is the Pauli Jordan. The imaginary part of the Feynman is the symmetric propagator. Make sense? Okay, it's important to commit it to memory too. The Hadamard. Okay. So once you have, if you use delta H and E as the building blocks, okay, then you can write the Wyman as that and the Feynman as that. So once again, there's a summary of the things. H gives you the symmetric correlation components. E gives the commutator, I call it content, but this is the commutator expectation. And delta is the symmetric combination of advance and retard propagation. Okay, cool. A little bit, this is something to keep as reference. It would be, it's nice to have it. It's posted in, you have the slides, you have it posted. But indeed, you can, and it's also important, is oftentimes it is the case that you will see books or people, because books are written by people and people speak to, call these things, all of them, green functions or propagators. They would call all of them that. It's a thing. If you go to even textbooks by extremely respectable people like Fulling, you get the textbook by Fulling, Fulling calls them all green functions. Well, technically, only these three are green functions. These are kernels. Kernels means that they are solutions to the equations of motion, so solutions of the Klein-Gordon equation here. So this, the Wyman or the Hadamard or the symmetric propagator, they will be solutions of the Klein-Gordon equation in both variables, whereas these guys are solutions of the delta-sourced Klein-Gordon equation, which is the green equation. Make sense? So technically, these guys are what we call propagators. Now, of course, that said, come on, E is the sum of two propagators, sure. But let's, mathematically speaking, only those are green functions. Make sense? All right. Of course, you can write, this is just to have as well, you can write all of them as a function of the others because they're all related, right? So you can write, for example, if you want, you can write the retarded propagator as a combination of the Feynman and the Wyman. Why not? Okay. Let's talk a little bit, before more general structure, let's talk a little bit about the Minkowski, the Weyman function in Minkowski with the complex structure associated, the complex structure that gives you the vacuum that has all the symmetries of Minkowski. Okay, so what we call the Minkowski vacuum, which is the state that has all the symmetries of the theory, Poincare invariance state. Okay, so I picked a particular complex structure. And let's talk about it. So first of all, is time translational invariant and spatial translational invariant. There's space-time translations. That means that that thing should not depend on t and t prime, but on the difference rather, or x and x prime, but on the difference rather. This, when that happens, we say that it's time translational invariant or stationary. Make sense? For Minkowski, for the Minkowski vacuum. Now, this is interesting, right? Because I add this. All expressions are understood with that prescription. Now, I don't know how much distribution theory you have seen. But let me just talk for fun about a little bit of something. How familiar are you with the notion of Cauchy principal value? Very? From 0 to 10? How many tens? 1, 2. How many fours? 4 or lower? Okay, then I'll talk a little bit about it. Okay, so you're going to learn it in this course, which is nice. And you're going to learn it by doing it. It's not really necessary to understand this. Usually, you have two options to work with these things. You do Fourier transforms and you work in the Fourier space where complicated distributions become more function-like. Or you do residue theorem integrals, and that works too, more work. But to understand truly this object, you need to understand a little bit about distribution theory. Otherwise, it's a bit of hand-waving here and there. Okay, integration by parts and residue theorem and hand-waving to say that the things are well-defined. I'll give you a little example with Cauchy principal value. And then I'll introduce Hadamard finite parts. You have this guided tutorial, an assignment that is guided and introduces all these notions a bit better, right? But once again, imagine, those of you who know, don't spoil it, because I think it's nice to learn it, because I think Cauchy principal value in the principal value integral of 1 over x kind of distributions, that thing links physical intuition with the distributional theory math that's behind it. So I think it's a nice example. Say that I want to do this integral. I don't know, for example, from minus 1 to 1 dx 1 over x. What's the result of doing that integral? So those of you who don't know, you have to answer this question. You're teaching calculus to a first year to get some money on the side. And it's a good student, and they ask you this question. What is the value? Is this defined? What is the value of that? What would you say? I take suggestions. You say 0. Okay.
Undefined.
Undefined. So I was hoping that there was some mathematician in the room, and they would tell me, this is not well defined. This integrand is singular at 0, no? But then there's some argument for, well, you said you know. Okay, so there's an argument for 0, no? If you're not a mathematician but a physicist, there's an argument for 0. What would be the argument? Who can make it? A argument, yeah.
It's like an odd function, and you have
right? So you have this thing. I am not the best at drawing, as you probably know by now. But you have things like that, these things minus infinity, kind of like that, no? And you say, well, this area and this area is the same, so it's 0. No? Negative and positive, so it's 0. So I would even be, if I'm the student, I would be even more questioning that. Is that 0? So the idea here is very intuitive physically, but then the mathematician would say, that's not well defined, that's bullshit. I shouldn't say that. That's BS, you cannot do this. But then you say, oh, come on, I'm gonna write it in a way that you'll be happy with. And the way could be like this. You may have to help me with the arithmetic as usual, but the way could be like that. What if I do something like this? I decompose the integral, let's call it I, and I decompose the integral as the integral from -1 to epsilon dx 1 over x plus the integral from epsilon to 1 with epsilon larger than 0, right? dx 1x. Now, this is well defined. No mathematician would object to that. There's a positive limit here. We don't cross the singularity.
Should be minus epsilon on the left.
So, of course. Thank you. Nobody would be objecting to that. But then you say, well, but the mathematician would say, yeah, but that's not that. I say, wait. What if I do this? The two things should be maybe the same. Maybe. And then you continue. Mathematician is looking at you, and you can see in the face that it's not going to work. But it's looking at you, right? And then says, and you say, okay, let's do this. So this thing, so the integral of this guy is the log, no? Well, the ln, as you would say, the natural log. For me, when I write log with nothing, I mean natural log, okay? So that would be the log at epsilon minus the log at 1 at -1. And I get here a plus the log at 1, and here I get minus the log of epsilon. No? Something like that?
Should be log minus epsilon if you're saying.
It's the absolute value of. Yeah. So the nice thing about that is that the log of epsilon cancels and things are well defined, and log of -1 is not the minus log of 1. What am I doing wrong?
It should be log 1 for log -1. Absolute value of.
Say again?
Should be absolute value of.
I forgot the freaking absolute value. Thank you. Minus and plus, and this, sorry, yeah, that's it. And this cancels that, and that's 0. Make sense? And then you are very satisfied with yourself because you say, aha, this is a rigorous way of regularizing this in a way that matches the physical intuition. But then the mathematician friend looks at you and said, this is BS. Because if you say that these two integrals are the same, then it should also be the same if I write here to epsilon. No? The limit should be the same. But if I do that, then I have a to epsilon here, and this is not 0. So your choice of this kind of regularization is BS, because the interval was not defined to begin with. End of question. If you treat this as a function, as an integral, then as an integral of a function, this is not well defined, and all the things that you did are not great. But then you can say, okay, how about this? Let me treat this integral not as the integral of a function, but let me treat this as some notion of action in a test space, and this is a distribution. So this thing is going to be multiplying functions that are so that the total integral is going to be well defined. And let me prescribe this integral as the symmetric prescription, so this one, by definition. And if I prescribe it as the symmetric prescription, then I can extend the theorems of complex variables that work for functions. I extend them to work for these kinds of distributions. This is the Cauchy principal value prescription in a nutshell. It's a bit more rigorous than that, and you'll see it in the text. But that's the one. That's the one that gives you the residue theorem to work well. So it's a definition. In a way, I say that I define this guy as the principal value integral of that, and PV means these limits. Make sense? All right. Well, as I said, it will be explained in the tutorial and assignment parts that are needed much better, but at least you get an idea. Can we switch off the lights? Thank you. So the idea is to make sense of. It didn't switch off.
I think the god turned it off and then we
Ah,
Oh, thanks God.
nice. That's awesome. You see, this is not a unitary action because it's a larger Hilbert space where somebody else turns off the light. All right. All right. So every time that we're going to have things that are divergent, like if you have things that are divergent, as you can tell, this 1 over rho, you get that this 1 over rho at the light cone is going to be something that goes to 0, and therefore this expression would be divergent. We add this kind of regularization, and that kind of regularization is saying this is a distribution, and you have to understand distribution now as the generalization of this for arbitrary functional dependence of things that go like 1 over x to the alpha, where alpha is any real number. And we call that generalization, and you will see it in the assignment, is called Hadamard finite part. Hadamard finite part is related to Hadamard finite part is related to the principal value. For example, for integer powers, if you have an x squared, so how do you do it? You have an x squared. If you have an x squared, well, you can relate it to the principal value by doing integration by parts. If you multiply it by a function that is going to decay to 0 at the boundaries, at infinity, if you integrate infinity, then the integration by parts, the boundary terms, you cancel, and then you are left with the derivative of this guy, and the derivative. Can you turn it off?
No, it's fine.
No, wait. The wrath of the gods. Anyway. So you can use integration by parts to relate the two, okay? And again, that will be explained in the text that you'll get in the assignment. It's not that important. It's only important because you're going to do it in calculation, and please ask questions. So it's not that important to understand the concepts, but it's nice to be able to do it. And distribution theory is super cool. You will see how cool it is when you do it. Can't emphasize how cool it is because, fun fact, when you get integer powers, so if it's 1 over x to an integer power, you get this kind of principal value singular part plus a delta, which I will not mention. There's a singularity part that comes with a delta. And when it's any non-integer, for example, the square root that is half integer, it's a branch cut. I don't know how much complex variable you've seen, but I promise to you it will be fun. Yes, if it's not fun, you can tell me off and ask me questions. It should be fun. You should be having fun with it. It's not meant to grind you. It's meant to for you to enjoy it and see, oh, gee, complex analysis is so cool. When you mix complex analysis with distribution theory. Anyway, this is something that you will compute for a massive field of mass m. This is the Weinmann function. For Minkowski, massive field of mass m in m plus 1 space-time dimensions, so n spatial dimensions. It looks like that. Kind of complicated, but committed to memory. We may use that expression eventually. I'm going to save you from the calculations until you do an assignment. There will be a bonus question, which is computing this, I think. So you can tell that guy, right, that we have is the Lorentzian square interval. We'll talk about Sinch-Wolf function in a second. But of course, rho square is larger than 0 means that you're in space the points are in space-like separation, and less than 0 are in time-like separation. So the I epsilon prescription, what it does here is selects the correct boundary value across the light cone. So what happens on the light cone? It would be singular, but you need to check what boundary value it actually represented. It's a distribution. So you see the Weinmann as a function will be divergent on the light cone, but that makes no sense. It's not meant to be a function. It's meant to be integrated against other functions. It's a distribution. All these things propagate things. They're meant to be integrated against something else. Okay. You could get the massless limits very easily. Again, that would be also a bonus in the assignment by using the asymptotic expansions for the Bessel functions. And then you get that for n larger than 1, this is what it looks like. This gamma is the gamma function. So this thing you may recognize as being related to the volume of the sphere. It's proportional to the volume of the sphere. And it looks like that. It looks like 1 over some power of the space-time interval between the points times some geometric factor with the epsilon, with the I epsilon. This is important. Now, you can write those things as distributions, and I'll show you a little bit of that. But the idea is that for n larger than 1, the Weinmann function is a pure power law. It's let's say that it's got a singular, well, it's actually we call it a regular part, but it's got a part of it that goes like 1 over the space-time interval to some power. And the power is higher, the higher the dimensions. Make sense? In 1 plus 1 dimensions, one has to be careful, right? In 1 plus 1 dimensions, if you do it again, it's also part of the exercise. But in 1 plus 1 dimensions, the Weinmann functions looks a little bit like that, and is IR divergent in the massless case. So if you are doing a massive field, fine. If it's a massless field, you need to introduce an IR regulator. I could speak days about infrared divergences. It's the first thing I did in grad school, actually. Like, look at infrared divergences. They're cool. They're often ignored. I don't know, in your QFT courses, in S-matrix, they exist as well. Have you talked about IR divergences? Have somebody told you that there's no cure for them? No, I told you there's no cure for them. Any of the methods to renormalize IR divergences is different ways of summing a divergent sum, rearranging the terms so that you get something convergent, but you could get many different ways of combining that. But anyway, I will not talk. In 1 plus 1 dimension, you get IR ambiguities, which makes sense. In 1 plus 1 dimensions, theories are IR divergent. There's no scales to help you. Let's look at the massless cases. This is the stuff that you're going to deduce, that you're going to prove in your assignment. Let's quickly walk through the explicit expressions of the 2-point functions in flat spacetime in the massless limit. So in the massive limit is that boring expression with the Bessel functions, right? Things become so that is a function. You see that, well, again, not quite. If you write finite part in front, that's a function. But it's a boring one. It becomes super interesting in the case of massless, the massless case. And it's kind of super cool, right? Because they behave extremely different, and that's super important in RQI and in many cases in many of the phenomenology. The distinction, even in flat spacetime, the singular part, if you want, of the Weinmann function and the Feynman behave, it's different in even versus odd spacetime dimensions. In this course, I'm going to use n for spatial dimensions and d for spacetime dimensions, okay? So you see a d means spacetime dimensions. Let me show you. These are the things that you're going to calculate in the distribution theory assignment that we have. So the Weinmann functions, plus and minus, plus is the Weinmann, minus is the conjugate of the Weinmann. It's often notated with a -2, okay? It looks like this. I think you're going to do it only in 3 plus 1 dimensions, but this is for arbitrary dimensions. Look what it looks like. You have a part here, this sigma. Oh, I didn't define it. I should have defined it earlier. I don't know why I didn't define it. But this sigma is Saint-Wall function. It's the space-time distance between them. Okay? It's the space-time interval between them. Between x and x prime. But you see, it looks like you get some finite part. Think of it as like that, some principal value part. That is a regular distribution. We call it regular. It's funny enough. We don't call it divergent. We call it regular. Even though it's... Again, is the finite part. The finite part is the generalization of principal value to higher order polynomial dependence. You can think of it, if you know complex analysis. Everybody here has seen complex analysis? If you know complex analysis, this is take the Laurent series of that, subtract the divergent contributions of the Laurent series, and continue with the rest. Kind of. That's what it is. And you will see it is defined rigorously like that. And that we call it, it's actually, finite part is called Hadamar's finite part. The same Hadamard as the H. Okay, makes sense? So the finite part, which is again the generalization of the principal value. For example, if this was something like 1 over x absolute value, that would be a principal value. But it's not. It's higher order polynomial. Sigma already has a square. Sigma is the space-time interval. It already has a square. So it's got this part, but also got something that goes with derivatives of the delta. In 3 dimensions, 3 spatial, so 3 plus 1, yeah, 2m. Okay, that's not 3 dimensions because we do in even space-time dimensions. Oh no, that's fine, yeah. So in 3 dimensions, this is the derivative, so this should be, no, it's half, okay. In 3 dimensions, this is the delta function. This means derivative of the delta, the m minus 2 derivative of the delta. So it's a delta function times a sine. We call the delta part the singular part. The part that goes with derivatives of the delta, we call it singular part. And the other one is the regular part. Make sense? You know maybe why, right? Because one is kind of like smooth and going down, and the other one is a delta distribution. It's a peak distribution. Make sense? For the Feynman, same thing. For the Feynman, you get a real part. The real part is the same, as you can tell. Of course, that's the Hadamard. Remember, the Hadamard is the real part of both. This is the Pauli-Jordan. And in fact, you can already get, well, it's okay. This is the Pauli-Jordan. And this thing is the symmetric propagator. You see the difference is literally what we said before. The Pauli-Jordan is time antisymmetric, whereas the it's not coming back. It always happens in the worst moment. Okay, when things get the most abstract, you know? It's the same as the Pauli-Jordan, but symmetric. Makes sense. This is the delta. This is the they have the Pauli-Jordan. So in even space-time dimensions, this is kind of cool because the singular structure is localized on the light cone. Look at that. This is a delta on the light cone. Look at what that means. That means that the Pauli-Jordan, the commutator, in these cases, flat space-time, the commutator is 0 in the future and in the past. It's only non-zero in the light cone, which kind of makes sense, no? You would say a perturbation in a massless field, you think of it as it propagates at the speed of light. So the propagation goes only on the light cone, on the boundary. Yeah. This, what we call this, by the way, the strong Huygens principle. You know the Huygens principle. Huygens principle tells you every point acts as an emitter at the speed of light, right? As it propagates. It's true in even space-time dimensions. In odd space-time dimensions, and I don't want to give you many spoilers for the assignment. Okay, this is a 1 plus 1. Fair enough. So in 1 plus 1, there's a special case of even that is different from the rest because in this one you have a heavy side in the imaginary part. But let's not focus on this one. Let's look at the odd space-time dimensions. Look at the freaking odd space-time dimensions. The Hadamard doesn't look that different. The singular part, though, the Pauli-Jordan, the commutator, the thing that propagates. This is a classical problem. This is a classical issue, super interesting classical issue. This thing is not a delta anymore. In odd space-time dimensions, there's a heavy side. This has to do with the fact that the distribution with the I epsilon, instead of having, you know, in the case of integer powers, you actually have poles. Like in complex variables, you have the 1 over epsilon kind of distribution has poles. When you are in non-integer powers, you don't have poles, you have branch cut singularities. And the branch cut is a jump, a discontinuity in the phase. And that's what gives you the freaking delta. This is an imaginary part. So the branch cut, you put it on the, for example, the left semi-axis. Then when you jump through the left semi-axis, when you switch the sign of the eye, you get a phase, an extra phase when you move. If your epsilon is going up versus not going up, there's a jumping phase. And that will give you the heavy side instead of the delta. The delta appears when you have poles, the heavy side when you have branch cuts. Fun fact, the branch cut one is actually much simpler mathematically to do than the poles ones, because the poles one you could do it with the residue theorem, for example. This one is just, you can draw it in a diagram and see what, oh, I'm missing, yeah, it's a pi if the epsilon is, if it's plus epsilon, but it's nothing if it's minus epsilon. Okay, so if you have a time component, if you are above, if your space-time interval is above, then is the phase with an extra pi, and without the pi when it's below, and that's why you get the heavy side. You will see that. But look at that, man, this is crazy. The 2-point function in odd space-time dimensions, and in 1 + 1, which is even technically, but it behaves like this, the Pauli Jordan has support in the whole of the future and the past, not just on the boundary of the light cone. And this is a massless field we're talking about. Massless field, let me tell you, there's a protocol in relativistic quantum information that I'm not sure if we have time to talk about. So I'll tell you one thing. Imagine that I get a flashlight and I want to use it to send signals to somebody sitting on that chair over there, the one at the corner there. Maybe I should send it to you because you're actually a person. So with the flashlight, I send light, right? And then if you are there exactly on the light cone of my signal, you see it, no? You get the information. I send you light travels at the speed of light, no faster, obviously, but also not slower. It's a massless field. So it goes at the speed of light, and you received it. Now, here's another thing. Imagine that you're not here, and I get the flashlight and I send you information. But an hour later, you come here and sit down there. Can you read the signal? No, because the light is gone. Well, in 3 + 1 dimension Minkowski, yes, that's true. Anything else but even space-time dimensions larger than 1 + 1 Minkowski, and you can, because the freaking signal makes a disturbance, an echo, an afterglow. That's what they called it in PhysOrg, an afterglow of the signal that stays there. And it's conceivable that you can come later on, do something, and read out that freaking information. And it comes from the classical structure of propagation of solutions. Look, the strong Huygens principle, which is the one that is intuitive, the one light just goes at the speed of light. I have a bunch of slides on this. That I can, for illustration. Yeah, here. This one. I always do it. It's a bit of a facetious thing, but anyway. General properties of wireless communication. What I tell the audience usually is this, without telling them about distributions first. I'm going to tell you a bunch of things that are reasonably true for wireless communication. Then you tell me if you agree or disagree. And I say, communication mediated by real energy carrying quanta, at least on average, meaning that you need to send energy in order to send information. This is the number of times in physics you hear that. Maybe you agree that if I'm not coming, I will not send any signals. Fine, but on average, if I keep repeating every day, at some point I have to send a signal, and the information should be carried by some energy, no? So an emitter emits photons. Look, I hate that. A receiver captures photons, kind of philosophy. Another one, information flow has to be carried by some energy flow. You cannot communicate without establishing an energy flow between emitters and receivers. No, information reaches you when energy reaches you. Maybe that one is easy to convince people to, but even classically, you already know that maybe. Okay, no. This one. Communication is only possible at the speed of light in vacuum, right? Meaning not faster, obviously, but also not slower. Meaning that if you miss the beam, you miss the message. And then I put them all together, and I usually say, do they seem reasonable? And then people say, yes, they seem reasonable. And I say, well, in this talk or with this protocol, I want to convince you that actually they're all false, all of them. And the idea is, the idea that we use, we call this protocol when we introduced it, quantum collect calling. The reason for the quantum collect calling is because the emitter does something, spends energy, the energy goes at the speed of light. As to see, the stress energy density depends on derivatives of the field amplitude. If I vary the amplitude of the field here, the energy goes with the derivatives only. So the derivatives only are non-zero here, and remain constant here and here, goes at the speed of light. But somebody in the time-like future can do something, they spend the energy to do something whenever they want, and they can recover the message. Which is crazy in many ways. But that protocol called quantum collect calling uses something very classical, which is the violations of the strong Huygens principle. In fact, yeah, that's kind of cool. I didn't mean to show off here, but it was nice. They call it afterglow. I like the afterglow thing. But yeah, the strong Huygens principle that says the green functions of the massless wave equation in 3 + 1 Minkowski has support only on the light cone. Hence, any disturbances propagate strictly along null geodesics. That's false in general. Well, it's true, as stated. It's not true in general. The moment you relax any of this, Yeah, I didn't say. No technical details, only if we have time. But the point being, right, that is the stuff that the propagation of information is not suppressed inside the light cone, which is crazy. And now you say, okay, how often do you see violations of strong Huygens? I would tell you, well, already with odd space-time dimensions, any flat space-time with odd space-time dimensions. In curved space-times, almost always. And I'm not talking about light cones being curved, being tilted. I'm talking about really the propagator having support on the boundary or inside the light cone. In fact, mathematicians that study this, they call it the Thales problem, by the way. Mathematicians who study this, violations of strong Huygens, what they want is to find space-times for which is not violated. Look how rare it is. Minkowski even, yes, but extremely rare. For example, in FRW, don't quote me on this because I don't remember the exact case, but there's one case, which is, I think it was a matter-dominated universe where the mass equals to some proportional constant of the Hubble length. So again, it's rare to have strong Huygens principle. The norm is actually that it's not the delta-like, it's like this. The delta is the intuitive. I want to say the delta is the intuitive. I do something in a massless field, perturbation goes at the speed of light only. But the most common ones is the heavy side. It's crazy. You will see, if you do the value of doing the distribution theory exercise is to see how freaking fine-tuned is the case of Minkowski even, that you get a single pole or double pole, depending if it's Feynman or Wyman, single pole or double pole singularities, as opposed to branch cuts. Branch cuts is the norm. The other ones are exceptions. We are in a very special. And then you can use this, if you engineer effective lower dimensions and optical fibers, waveguides, you can get strong Huygens principle and stuff. Anyway, I may talk about quantum collect calling only if there's time. That's why I introduced a little bit. But it connects to that. Now that's clear that you get this anomaly in the classical stuff of the theory already. And you can exploit it to send information with quantum theory. All right. Same with the Feynman, right? Yeah, I mean, I even say it here. Remember that I did it on the fly, but I have it here. It's time order symmetric. And of course, the orientation is doubly, the one that's not time order symmetric. Anyway, the same happens with the Feynman, of course. Notice, by the way, another thing to notice is neither the Wyman nor the Feynman cancel outside of the light cone. This thing has support everywhere. Agreed? This is non-zero in space-like separation. Agreed, everybody? That's going to be important as well. Nice observation. The causal propagators, oftentimes we use the name causal propagators, even if they're not propagators, because usually propagator is synonym with green function. But we call the causal ones the ones that actually are zero outside of the light cone. Those are the advanced, the retarded, the symmetric, and the Pauli Jordan. The other ones we don't call the causal propagators. Make sense? Good. Yeah, well, this is the summary of the whole story that I just told you, showing you like the Abraham Lincoln kind of thing. Yeah. All right, so you will do a little assignment, homework, plus tutorial on this stuff, and hopefully you will get to enjoy the distribution theory part. I know Irini loves it, and that will be Monday mostly, distribution theory part 1. The Thursday one with Mateus. Mateus also loves it with the kind of love that you have when you write papers on that stuff, and you spend a lot of time battling and frustrated with the distribution and so on. And then you love them, but it's a different kind of love, if you know what I mean. Okay, so for even space-time dimensions, the singular parts. So remember, what we call the regular part, the finite part, right? That has support everywhere. But what we call the singular part, as you know, is related to the Pauli Jordan with causal propagation of stuff. That has support only on the boundaries of the light cone, and the imaginary part involves derivatives of the deltas. In flat spacetime, odd dimension, the support is always inside the light cone, and you have power law tails appearing in general. Good. Any question? I mean, again, this is formal stuff, but I hope that these points tell you that that's going to be important when you want to do informational stuff in space-time. For real, you want to put qubits in space-time and be relativistic and use field theory. Those things matter. Make sense? Okay, I hope you see. Okay, let's talk about one last thing before we move.
It's good stuff.
The Hadamard condition. Okay, so let's go back. Let's not show that first. Let's discuss a little bit, remembering what we did. Remember that to choose a vacuum, we have to choose a complex structure, right? Choosing complex structure, same as choosing a vacuum, 1-to-1. Remember that for any pure state that is reasonable, you can always find a complex structure for which that's the vacuum. Makes sense? You got any state that you want, right? And you can find creation and annihilation operators of them, so that you recover, go back and do the construction of the complex structure. Always possible. Well, always possible as long as the state is reasonable. What do we mean by reasonable? So people like Hadamard and others, Whiteman, many others, like Chris Fuster, also contributed to general characterization. Chris Fuster is a professor in York, is amazing. So if you like algebraic QFT and want to explore more of that, Chris Fuster is a great person to talk to. So the Hadamard condition is precisely the conditions, and what do reasonable states have to have in order to be able to say that there could be a vacuum that's reasonable, that nothing weird happens. And the condition, the Hadamard condition, let me put it like that first. We say, so this is something for curved spacetime in general, okay? Now, Minkowski illustrates a lot of things, but this is more general than that. A quantum state is Hadamard if its two-point function has the same short-distance singularity structure as the Minkowski vacuum. Meaning that if I zoom in a lot, it needs to look like the vacuum on Minkowski. That kind of makes sense, no? Physically speaking, you have a very rough space-time. If you zoom in a lot, it's going to look flat. If you have a very weird state, if you zoom in a lot, it's going to look like the vacuum. You get into the UV. In the UV, if it's reasonable, it should look like the vacuum. So that's the idea. So in the coincidence limit, which is the UV limit of the theory, the extreme ultraviolet limit of the theory, you want the singularity structure of the two-point function to be the same as Minkowski. That's the Hadamard condition. So the singular structure is fixed by geometry, as we will talk about, and all physical states must share the same UV behavior. That's the idea. Nothing weird should happen in the UV for the Hadamard condition to be true. So difference between states should appear only in the smooth part, not the singular part. Make sense? This is basically saying the Pauli Jordan has to be this kind of delta or heavy side, and all the difference in the states should appear only in the smooth part. Okay, let me rephrase this with a little bit of physics here. Hadamard states have the corresponding distance behavior needed for renormalization. For example, another way to operationally talk about the Hadamard states are those for which the expectation value of T mu nu in the vacuum, once normal order, once renormalized, what is called the renormalized stress energy tensor, the expectation value on vacuum of that is finite. Make sense? Ideally 0. They look like this. The two-point function of a Hadamard state has this universal local form. With this, again, this should have been defined before because I've used it all the time. This sigma is Singes-Word function, so half the square geodesic distance. That's why you got 2 sigma. Have you seen Singes-Word function elsewhere? Okay, it's 1/2 of the geodesic distance. Okay, if you want. And then, of course, this is the epsilon regularized one. This is a distribution that we're talking about. So you need to add this epsilon part here. The square I add, you don't need the square, but I add it so as to be aware of the structure of the singularities. That comes from, okay, I'm going to leave it for the assignment and the discussion. The important thing is that the state dependence, so all the things, this part here that you see, this part here that has something that is, if you want, the finite part, if you want part, the part that diverges at coincidence. You see, there are two parts that diverge at coincidence, right? Part number one is the first one that goes like 1 over the geodesic distance, right? Then you get the logarithm of the geodesic distance, and then you get some other contribution that is not divergent in the coincidence limit. So the Hadamard condition tells you that you can write the Weinmann function always like that, and the regular part survives the coincidence limit. All the singularities in the coincidence limit are in what we call the geometric part, if you want. Make sense? Any questions? So all Hadamard states share the same singular structure. They differ only by a smooth function. That's the idea. Yeah.
And by the geometrically determined, you mean like it depends on the space-time in which we are.
Totally. In those ingredients, you have the Van Vleck determinant. You have several things that depend on G, on the metric. Well, also you get sigma, which obviously depends on the metric. Sigma is the contraction with the metric of the. Make sense, everybody? Okay, so it's important to keep it in mind, this idea of Hadamard state, because have you ever heard this? The trend is gone, I think, now. But have you ever heard about firewalls? So if you hear about firewalls, the idea of firewalls is one approach towards the information loss problem. You know about the information loss problem in black holes, which is the summarizing a lot and not getting into a ton of the details. The idea is, all right, so evolution is probably unitary if everything is quantum. So if I toss something that has correlations into a black hole and sending information to the black hole, I'm losing information here where the unitary evolution cannot destroy information. Hawking radiation is thermal, so it looks like it's not going to contain enough information to recover all the information you threw out. Thermal is the most scrambled that you can be, the least information that you can have, right? If the black hole eventually evaporates, where did the information go? Is there a remnant? Well, there's a problem with it being a remnant, okay. Is the information lost? Well, then there's a problem with quantum mechanics. Quantum mechanics should not allow for information being lost. One of the proposals was, there are many ways around this, right? And we can talk about that if you're interested in the discussions. But one of the proposals around it was it's very famous some years ago, the idea that there's some violence happen at the horizon. You know, there's nothing should happen at the horizon. In GR, there's nothing weird happen at the horizon of a black hole. At least, well, think of Barsil to begin with. Nothing weird happens at the horizon. But the idea here is that, well, what if there's a firewall, meaning that divergence of the stress energy density, something violent that happens at the horizon that somehow erases the information? Well, firewall states break this. They're not Hadamard. And it's kind of funny. I can build you a firewall state very easily. Say Minkowski, and I have the Minkowski vacuum. Say that I get these two wedges, right? 1 and 2 as before. And then I say, okay, I can call the state of the field here rho A or rho 1, and this rho 2. And that state rho 1 and rho 2, well, rho 1 is of course the trace over 2 of that guy, no? Agreed? I just erase everything that's in here. The idea of the firewall state is replace the Minkowski vacuum. This is a firewall state this is called the Rindler firewall, by the way. Replace it by rho 1 tensor rho 2. Meaning, I replace the pure state that we had before as the tensor of two mixed states on each side. Look, if you live locally on this wedge, you would not be able to tell it's different. In each of the wedges, it's exactly the same as the vacuum. But what you've done is you broke, remember all the entanglement that there is between the two? Remember the two-mode squeeze state that I showed you, a lot of entanglement? I broke it. I broke the whole thing. What is the price you pay if you do it? Well, you get a firewall in the Rindler horizon. This thing, the stress energy density is divergent on the firewall. That is not a Hadamard state. I don't like the firewall solution to the information loss problem. I think it's very bad. I wrote a PRL criticizing it, so I should be in my position with Jorma. Any questions about the Hadamard condition or anything else that we see? So I know this is dense. The slides are already, and I corrected a couple typos, but you have a version. I will send another one of this already uploaded to the portal. Any questions before we move to the next thing? I am so happy to take questions for what is left. I can move to the next thing if there's none, but yeah.
I think the class is ended 15 minutes ago.
I always do the same. Very, very sorry about that. I always think this is crazy because I thought, oh, I don't think I'm going to have enough time to cover everything. I leave the hammer and everything, but it always happens. I think in my mind we start at 15:15, and that's why. 15 past. You need to tell me these things. Sorry about that. Yeah. No, you don't need to. It's definitely my duty, but I forgot. I was looking at the clock all the time, and I thought we ended at 15:15.
But we finished the slides, so it was good.
Yeah, no, I'm not happy about it. I don't want to overwork you. This is dense stuff. Any questions or anything? We're done. Any questions? Yeah.
With the whole like things don't propagate along light cones anymore, I guess first question is does
Well, they do, but also inside.
exclusively. The first question is if you have like a space-time structure that's like some manifold, like a sphere, and then times r in the time direction, does that also
Not the same. I'm talking locally. So this is on top of that.
no, but I mean you said like for curved space-times it usually doesn't work. So
The Huygens, yeah. No, it's not because of that. Locally, it doesn't work either.
yeah,
Like
but, I mean, but like if your space-time is a sphere times time,
Uh-huh.
would like so it would disperse and not follow light cones along that space-time as well?
In general, yes.
So, and then does that come from if you have like solutions to the wave equation, like a delta just moving along isn't a solution anymore?
To the Green's function, to the Green's equation, not the equation of motion. These are the Green's functions that have that. It's the imaginary part of the Weidmann.
Yeah, but like I guess in Minkowski spacetime, like just a delta moving at like a constant speed
Yeah.
is a solution to the wave equation.
Yeah.
So
But also in higher dimensions. That's true in in any dimensions in Minkowski.
yes,
Yeah.
and then that lets you reconstruct any solution by just integrating that against like the Green's function against that.
Yeah.
So on manifolds that aren't flat, does that mean a delta function moving at a constant speed is no longer a solution?
You have to have a spherical delta, so it would be something like a delta would exist, but it wouldn't be just a delta. It's a delta. I'll have to do it because there's extra derivatives. I don't know what the factors would be, but you can have something like a delta, something pointed like a delta, and then with extra factors on top, yeah, as a solution. But that's not what we mean here. What we mean here is that if you make a little perturbation, right? The propagation of that perturbation filters into the light cone.
Yeah.
That's what we're. So there are two contributions to this. Contribution number one, if you want, is there's only one effect here, but it should not be confused with something else. Something else is if I have a curved space-time, you can have that the light cones curve, right? And because the light cone curves, you may have even that you have two geodesics, two different geodesics that connect 2 points, for example. And then you can say, well, maybe one is a bent light cone in this direction, the other one is a bent light cone in this other direction. This is different from the strong-Huygens violation. The strong-Huygens is the quasi-local region.
Yeah.
Okay.
Sorry, if
Yeah.
I may add something. So I've in the past worked on something very, very similar to this. You took you coupled two particle detectors on a scalar vacuum on S2 cross R, and in fact you see exactly this. If I treat the excitation probability of the second detector as a proxy for the field, and I get
Yeah.
excited or involved in a sense because of the first detector coupling to it, you see exactly the structure. Like you quite literally start seeing, if you pick up foliation, you start seeing a thing that propagates throughout
Yeah.
the space-time,
Yeah.
the spatial part, that's not just entirely.
But that is different from what you said. A delta-like solution would exist, can exist, something that looks like a delta, but this is different. You make a small perturbation, the small perturbation resonates throughout the light cone, not just propagated by the boundary, even in a massless field. Talking in terms of detector is less helpful because we haven't seen it, and we haven't seen it yet.
I know, but it's, kind of as a proxy to that, you definitely see that structure. And then, sorry, the other point you were making, kind of the distinction between what happens inside the light cones very locally versus, for example, if I have crazy black hole space-time and geodesics will go around, so I do something, it comes back, sort of, I see. That's
Yeah.
different from that.
Yeah. So between me and some other point, right, there can be two geodesics, right? One or many more. One that is direct, if you want, another one that goes around the black hole, winds several times, then touches it. Yeah. And technically, you could say, oh, this is like the quantum calling because I already sent the signal, but then it comes back later. No, that's different. Yep.
Sir, I'm still I'm worried because
B, yeah, nice. That's good.
the W thing,
The W thing, the Weidmann.
the Weidmann in the odd space-time dimension.
Let's go there.
How do we resolve the fact that it seems to be propagating faster than the speed of light?
What do you mean? Nothing is propagating.
Or like,
The Feynman propagator and the Weidmann propagator have support outside of the light cone.
yes, is that not concerning?
No.
But it kind of violates the
No, what?
not violates, but it violates my intuitions.
Does a plane wave violate your intuition?
But it goes at the speed of light, so it's okay.
But it's everywhere.
That's true.
No, it's okay. We will see. We're going to have, I can show you, for example, I mean, when we say particle detectors, if you couple to the field, you're not going to be able to use this to signal anybody. The signals only travel at the speed of light.
Okay.
Yeah.
I see.
I think the confusion comes confusing signals with correlations. There are correlations in space like separate. I don't want to spoil it too much because I was going to talk about, but I'll tell you something. This is a correlation function. Correlation functions can be non-zero between 2 points for two reasons. Because there's communication. Of course, I can get correlated with you because I talk to you. But also, maybe we are entangled for some reason. Like these guys, space like separated but entangled. So our correlation function, if we are entangled, will be non-zero, even though we're space like separated. You see, so correlation functions should account for both. Correlations that are not connected to the causal structure and the fact that they can communicate. So, spoiler alert, there's a protocol in RQI called entanglement harvesting. Entanglement harvesting is such a spoiler, but entanglement harvesting is related with having things that are space-like separated and they become entangled without exchanging signals while remaining space-like separated, without communicating. Detector A cannot tell that B even exists, and yet they can get entangled. And that should have been a question that leaves you concerned for 20 seconds and then explain how. But if I tell you how now, then I lost the power. But the reason that I'll tell you, not my power of the statement. The reason is that you are extracting correlations from the field. The field here and here is entangled, so you're swapping that entanglement to your detectors. So this thing is non-zero. If the Weidmann function were zero in space-like separation, you may get something like the firewall state. And that is not Hadamard, that's not a reasonable state. Any state that is reasonable, and this connects with there's something called the Rik-Leader theorem even, that is, take that to the max. A Rik-Leader is spelled like this. That theorem is take this to the extreme. You guys know a protocol in quantum information. I don't know if you've seen it. In quantum information called remote state preparation? No? Then it's less. The idea is that any state that is Hadamard, that is nice enough, is going to have a lot of entanglement between space-like separated regions. And this correlator not being zero then is a reflection of that entanglement. So there are two parts, a signaling kind of part, and you can identify the two more or less. Those are the right questions to ask. So I'm very happy, power speeches aside, I'm very happy you asked this question. Right. You have something about signaling, and you have something about the correlations in the field.
Sir, maybe this is because I have a misconception about QFT, or at least the way the QFT was presented to me. There was a statement, it's like, look, quantum mechanics is wrong because the expectation of a commutator is non-zero outside of light cone. So that's why we'll promote it to a QFT, and with a QFT, the expectation of the commutator outside of light cone will be zero. And so the expectation of a commutator is like a Pauli Jordan, which is the complex part of
It's literally the Pauli Jordan.
the Pauli Jordan. So looking at this,
The Pauli Jordan is 0 outside of the light cone. The imaginary part is the Pauli Jordan.
oh, it's 0.
Yeah. There's a delta on the light cone. Sigma is the space-time interval.
Sorry, but for the odd space-time dimension.
Same. It's a heavy side instead of a delta.
Ah,
The heavy side is 0 outside of the light cone. It's only non-zero in the future or the past.
oh, okay.
None of them. Okay, so you were worried about the imaginary part.
Yeah.
W, okay, this is important. W can be non-zero. This is reflecting the correlations. This one is the causal part. And this part is the commutator. This is the Pauli Jordan. And this thing is non-zero only in the light cone.
Oh, okay.
It's a heavy side. The heavy side is 0 outside of the light cone.
Okay, perfect. Okay.
Make sense? Something that is 0 outside of the light cone and decays like polynomially with a dimension in the massless case. Makes sense. Cool. All good questions. How you feel about the 2-point functions?
Disturbed.
Was that disturbed? Okay, that's good. But it's everything that I told you more or less assimilated, even if not fully understood yet. Okay. Please ask questions. This is good. This is very important, and it's important to look at QFT. The reason we do QFT, I would say it's a bit more deep than that. The reason we do QFT is because, look, you cannot do quantum mechanics of relativistic particles because you cannot localize particles. So what you need to do is go back and axiomatize what you want from a relativistic quantum theory. Make it axioms. And there are several axioms. And the axioms go at the level of the local algebras of observables. And one of those axioms is called microcausality, or Einstein causality, or Einstein locality sometimes. And that axiom tells you that the commutator of any elements of the local algebras, think of the field, for example, the field operator, the commutator of those has to have support only, so it should be 0 if the regions of support of the algebra are space-like separated. And then axiomatizing that, you get QFT from those axioms.
So it's saying that Pauli Jordan is 0 outside of light cone, essentially.
The Pauli Jordan is 0. Yeah, not only the Pauli Jordan, it's more general.
Okay.
But in a free theory, it's the same, because in a free theory, you can write any element of the local algebra as integrals over the field operators. If we had an interacting theory, it's not just the Pauli Jordan, you need more. Make sense? Yeah, like this is kind of fun, no? The QFT, the way I presented QFT, which is like from the basis, is like we have, okay, here's a question, and I think that your question is relevant because the motivation matters, right? Why did we do classical field theory instead of just mechanics of particles? Do you have an answer to that? Yeah, what do you answer?
I would assume like how spooky action at what did Newton call it? The thing that Newtonian's laws are instantaneous in time, which didn't make sense even to him, which caused us to go to formulate field theory.
So to get causality, you do field theory. So what I would argue is different from what you said. This is what I was after. In order to get a causal theory, we do classical field theory, relativistic classical field theory. And now we quantize that. And because we quantize that, the relativistic part is already incorporated in the classical field theory that we quantized. See what I mean? If you want to do it from axiomatic principles, then you have to postulate the axioms. But the way I did it, I started from classical field theory and I quantized it. So the classical field theory carries the burden of relativity, of causal propagation, let's say. Make sense? I just got a theory that was causally. So the way you said it kind of suggested that classical field theory violates causality. The way you said it. Because you said, oh, you have the commutator between. No, the classical field theory doesn't violate causality. The classical field theory, you get a Lagrangian that is Poincare invariant. So your equations of motion are going to respect Poincare symmetry in the flat spacetime case. Maybe your interpretations are bad. That I would not discuss. But that is true. Like for any equation of motion, if you're not careful, think of this. If you have the Klein-Gordon equation, and suddenly I give you, yeah, okay. I give you a solution to the Klein-Gordon equation. And I give you a solution such that it's compactly supported at time 0, right? So I get some initial condition, and I get it strictly compactly supported. Klein-Gordon without mass. With mass is fine, or without mass. And I give you something compactly supported. And I tell you, propagated with the Klein-Gordon equation in time. If you propagate that in time, you're gonna get non-zero components everywhere in space-time, everywhere in space, in the spatial slides, one instant after. Sure, they're tiny and they're gonna all propagate like that, but you're gonna get some. And the reason for that is related with the fact that that state that is very compactly supported, very well defined, is not well defined at all in the frequency spectrum of that. It's the problem of localizability. States that are too localized are not physical. So you have to be really careful when you talk about localization. You can localize a photon. This is a state in the single particle sector. You see, that's the classical, and I think that's what they meant. If you look at the Hilbert space in the classical theory, the one that you build with a complex structure, and you have a wave packet, and the wave packet is such that you make it compactly supported, it's going to have infinitely many, a distribution that is not suppressed fast enough in frequencies. So you're going to get solutions that are going to look like they move very fast, components if you want. They're going to look like they move very fast. So that is not a valid solution. So a single particle state is not physical. A single particle state that fits in a lab lives in that Hilbert space. The single mode Hilbert space is the space where a Fock state would live. So if you have a Fock state that is compactly supported, it will propagate acausally. In reality, you don't have that. You have something with infinitely many components of Fock components, not one particle, 1, 2, 3, 4, 5. And that thing can propagate causally. Or maybe you get something that is localized, not really localized, maybe it has tails, you know? And then if it has tails, it can live in that sector and propagate causally. But compact support and living in the one particle sector, bad. That's the problem of localizability. And that, the classical theory has it. And the quantum theory doesn't, because in the quantum field theory now we don't have a single mode Hilbert space, we get more than that. But you see, the problem is not the problem of the classical theory. Look, now that you know, who introduced the problem? Whoever introduced the complex structure and told me that that freaking thing in that Hilbert space is a physical thing. See what I mean? So it's not the problem of the classical theory. It's the problem of forcing an interpretation of particle to the classical theory that was never meant to be. That's why the classical theory has a problem. Once again, not because it's not relativistic. It totally is. You go to the action. So if the classical theory, the action, is Poincare invariant, then if you find non-locality of some kind, you made a mistake somewhere. The mistake here is I built a complex structure, I selected the plane waves, I have a Hilbert space, right, a single mode Hilbert space, and with that, I'm going to build a compact wave packet. With that, sir, it's not physical. It propagates causally. So again, it's trying to shoehorn notion of particle to a relativistic theory, you will end up having issues.